If the universe has an edge, what lies beyond it? Empty space. Other universes, or something we can't yet imagine. Tonight we'll journey to the very limits of cosmic understanding to explore one of science's deepest mysteries. If you enjoy these explorations, please like, subscribe and share, and tell us in the comments, what do you think lies beyond the edge? Thank you for watching. Now, let's begin. He stands within a vast changing volume of awareness that grows as time passes, though no surface marks its advance. The universe expands and light requires time to cross distances, so the most remote places that can affect this location are bounded not by a wall but by history. Cosmologists call this limit the particle horizon, the farthest reach from which any signal could have arrived, since the earliest instance when the hot young universe released light to travel freely. Beyond that reach, events continue, structures evolve, and light streams outward, yet none of it has had enough time to meet this small region of space. The horizon is therefore not a rim of matter or a cliff at the end of everything, but an ever-moving frontier where time and distance braid together. He notes that the frontier is defined by light itself. As space stretches, light waves stretch with it, so ancient signals arrive worn thin into longer wavelengths and softer colours. The faint afterglow known as the cosmic microwave background is the oldest light that can be seen directly with telescopes, a nearly uniform wash that carries tiny variations in temperature and brightness. Those variations, first mapped in detail by orbiting instruments, reveal seeds of later structure. They also draw a circle around the sensible past because before that light is released, the fog of early matter blocks any photon from crossing space unscattered. Photons then cannot deliver news from times earlier than that fog's clearing, which makes this afterglow a luminous flaw beneath observation. Yet the flaw is not the whole horizon. The horizon is deeper than the oldest visible light, because other messengers may carry traces from farther or earlier, and because the expansion of space means that locations can be out of touch, even if they were born together. He thinks of a common image to steady the idea: dots on the surface of a swelling sphere separate from one another without any dot being the central point. Each dot sees neighbours drift away, and the most distant dots disappear from view when the swelling outruns the light they send. No dot meets an outer edge on the surface, but each dot still keeps its own horizon of what can be seen and touched. The actual universe may not be curved as a sphere, and the image is imperfect, yet the lesson holds an observable edge is not a border in space, it is a limit born of time and motion. He considers words that often confuse. There is no centre of expansion in space, only a centre to each observer's view. If he moves 1 billion kilometres in any direction, the pattern of receding galaxies looks the same apart from small motions gathered in a local swarm. The horizon is centred on the observer, not because the observer is special, but because the horizon is defined by what can reach the observer. It is personal in that narrow sense and universal in every other. He watches another subtlety settle into place. The galaxies near the horizon are not frozen at its rim. They move in their own gravity fields carried by the larger flow of expansion, and by the time their ancient light reaches here, those systems have aged by billions of years. The horizon therefore shows not a shell of last things, but a shell of earliest arrivals from an ocean that continues far beyond. He recalls that the speed of light sets the pace but does not set the whole stage. The expansion of space can carry distant regions away faster than light without breaking the rules of relativity, because no object outruns light through space. Space itself stretches. That stretching draws a second kind of boundary into the story, the event horizon of an accelerating universe. An event horizon marks the limit beyond which events that occur now will never affect the observer, not even given infinite time, because the expansion outraces every signal forever. The particle horizon and the event horizon are not the same. The particle horizon tells how far the oldest accessible news has come from. The event horizon tells how far the newest news can ever go. Together they sketch a corridor of contact for any given place and epoch, and together they dissolve the idea of a final wall into a pattern of shifting reach. He lingers on the way evidence anchors this outline. Distant galaxies look redder than nearby ones because the space their light crossed has stretched a change, measured through careful spectra. Patterns in the ancient afterglow match predictions of an early hot plasma cooling and settling, with small imprints that grow into today's clusters and voids. On the larger scale, space appears close to flat, which means that straight lines behave as expected across great distances, though there remains room for gentle curvature that only deeper surveys can test. Each of these threads binds the horizon to measurements rather than to metaphor. Yet even bound to data, the picture invites wonder. The particle horizon recedes as time goes on, and more of the universe comes into view, but not in a simple way because the expansion rate evolves, and the event horizon limits future contact. There is quiet tension between the wish to see everything and the fact that everything cannot be seen from anywhere. He feels the scale of that tension when he imagines a galaxy whose light leaves today from beyond the event horizon. No instrument built in any future age here will record that light. The signal exists, it travels, but the river it rides widens faster than it can row. The horizon then is both generous and austere. It reveals enough of the early universe to map the rough blueprint of cosmic structure, and it hides enough of the total to keep the full territory unknown. He also feels the intimacy of the idea. The horizon is not only a line in the abstract, it is the shape of every night sky, the reason faint smudges at the limits of detection are windows into a much younger epoch, and the cause of the soft glow that surrounds all directions with origin and memory. It is the reason the word outside must be handled with care. There may be no outside in the sense of a beyond into which space spills only more universe that has not yet exchanged signals with this address. The question of what exists beyond the horizon remains open, not because a barrier stands in the path, but because time has not delivered the messages. As more messages arrive, the horizon moves, and what seemed a boundary becomes a milestone left behind, even as a different kind of boundary born of acceleration draws a line that progress cannot cross. The scene ends with this paradox held gently in mind. The edge of the observable universe is real and measurable, and yet it is not an edge of the universe itself. It is an appointment with signals kept by light and missed by light, an appointment that shifts with the calendar of cosmic expansion. He does not claim more than this for now. He notes the shape of the limit, the way it is seen, the way it is felt, and the way it hints that the true question is not where space ends, but how far connection reaches, and what subtle patterns at the farthest reach might tell about what lies still farther on. He faces the oldest light with patient instruments that rise above air and dust into darkness. This light comes from a time when the young universe cools, so that free electrons bind with protons and helium nuclei, forming neutral atoms and allowing radiation to travel without constant scattering. Cosmologists call that change recombination, though these atoms form for the first time. The released glow streams outward and stretches with space into microwave wavelengths, thinning into a nearly uniform bath that fills every direction. This ancient afterglow, the cosmic microwave background, carries tiny variations in temperature that trace small differences in density. Under gravity, those differences grow into galaxies, clusters, and the wide empty regions between them, So the pattern on this early sky becomes a blueprint for the later scaffold of the cosmos. In the hot young stage, matter and radiation behave like a fluid that rings with pressure waves. These waves set up peaks and troughs in density, and leave a signature in the ancient light, a sequence of preferred angular scales that careful observers can measure. Satellites operated by the National Aeronautics and Space Administration and by the European Space Agency map these patterns with rising clarity. The measured peaks point to a universe that is very nearly flat in its overall geometry, with only gentle curvature still possible, and they constrain the mixture of cosmic ingredients by how each one shifts the heights of the peaks. Before recombination, a more radical chapter unfolds that explains why the ancient light looks so even and yet not perfectly smooth. Inflation is a very brief period of accelerated expansion in the first fraction of a second when space enlarges by an enormous factor. It stretches any initial curvature so the observable region appears close to flat, and it turns quantum jitters in fields that fill space into macroscopic ripples, planting the seeds from which later structure grows. The tiny variations seen in the ancient light are then earliest imprint, not later noise, and they match the simple statistical forecast that inflation provides. A second hard-to-hear signal may also remain a relic pattern in the polarization of the ancient light that would show a faint swirling trace from gravity waves born during inflation. Teams on high plateaus and at the South Pole watch the sky through cold, quiet air to search for this pattern, while maps from space provide a full canvas on which to place any claim. Foreground dust glows and can masquerade as the target, so the search remains slow and careful. If the twist is seen without doubt, it would reveal the energy scale of the early acceleration and open a window on physics far beyond any laboratory. The ancient light has nearly the same temperature in opposite directions of the sky, even though without inflation those regions could never have exchanged information before recombination. Inflation solves this horizon problem by starting with a small patch in thermal contact, and then expanding it so rapidly that it grows to include the entire observable region today. It also addresses the flatness problem by erasing initial curvature and by diluting exotic relics that would otherwise linger in troubling abundance. Names aside, the picture is steady, an early universe smoothed and stretched just enough to plant simple, nearly scale-free conditions, then handed to gravity to do the slow work of assembly. Inflation leaves testable marks in the statistics of the ancient light. It predicts an overall closeness to Gaussian randomness, a slight preference for larger-scale power over smaller-scale power, and a near absence of distinctive non-random patterns. The observed ancient light follows a pattern close to Gaussian, with a small tilt that favours broad scales, while asymmetries and cold regions remain under study. Thus, the picture invites both confidence and curiosity. The horizon that matters at recombination is tiny compared with the size that inflation can produce, so the evenness of the ancient light feels natural in an inflated cosmos. Yet inflation is not a final explanation. It is a framework that points to fields and energies beyond present-day particles. Many models describe how the accelerated growth begins and ends, and different models predict small differences in the statistics that can be checked as measurements sharpen. Maps made above the glow of air tied to ground surveys that chart the three-dimensional distribution of galaxies allow a combined test the sky of the early time compared with the web of the later time. The two must agree on how initial ripples grow into present strands and nodes, otherwise attention turns to missing physics remaining foregrounds, or hints that the early story holds a surprise. He wonders what this means for the question of an outside. If inflation is not a one-time event but a behavior of space that can continue in other regions, then the smooth bubble that becomes the observable universe may be one region among many. Each region could hold slightly different details of its physics set by how the early field settles. The oldest light within one region will look even on large scales if inflation there lasts long enough, but the greater space beyond any one region could be patchy in its properties. The oldest light is therefore both a boundary and a clue a boundary, because it is the earliest that photons can show, and a clue because its delicate ripples whisper about a process that might continue elsewhere beyond sight. He does not claim a grand multiverse, and he does not deny it. He notes only that the mechanism which fits the evenness and the near-flat shape often carries a natural tendency to keep going in other places. What would mark this region as one bubble among many is not a slogan but a footprint, perhaps a circular bruise or a broad gradient in the ancient light from a past encounter. Searches for such marks have found no decisive evidence, but the maps improve the methods advance, and the question remains open. In this patience, first light and early acceleration join to define the edge as seen today. The ancient glow tells what the early conditions are, and inflation tells why they look uniform yet imperfect in just the right way to grow structure. Together they give the horizon a measured shape at once intimate and vast, and they hint that outside the horizon there could be more regions formed by the same process, separated not by walls, but by the simple fact that light and time have not yet linked them. He turns to the work of measuring expansion in the present day because the contour of any horizon depends on how fast space stretches and how that rate changes with time. Observers do not measure expansion by watching galaxies sail past with stopwatches. They infer it from light that carries both distance clues and the degree to which wavelengths have been stretched. The redshift is the change in wavelength imposed by expanding space, and it grows with distance in a way that depends on the history of the expansion. To turn a redshift into a distance, astronomers build a careful ladder where each rung checks the next. The first rungs are geometric. Parallax uses the orbit of Earth as a baseline to see nearby stars shift their apparent positions against distant backgrounds over the course of a year. The European Space Agency mission that maps star positions with extreme precision extends this geometric reach to many thousands of light-years. With distances to certain nearby stars in hand, observers calibrate variable stars known as Cepheids, whose pulsation periods link directly to their true brightness. When a Cepheid is seen in a distant galaxy, its apparent brightness reveals the distance to that galaxy, because the light has spread over a sphere that grows with distance. Massive sources in orbit around galactic nuclei give another geometric anchor, since the orbits can be measured and modelled to yield exact distances. With these calibrations, one can trust the brightness of Type Ia supernovae stellar explosions that serve as standard candles because they arise from similar starting conditions, and so share a characteristic intrinsic brightness. When such a supernova is found in a galaxy, the measured redshift tells how much the light has stretched, while the apparent brightness tells how far the light has travelled. Plotting many such events across cosmic time lays down a curve that reveals how the expansion rate changes. A second independent approach uses standard rulers imprinted in the distribution of matter. In the hot early plasma, pressure waves travel outward until recombination, leaving a preferred separation scale between overdense regions. This fossil scale, called the baryon acoustic feature, remains in the way galaxies cluster today. By measuring how this feature appears in surveys that map millions of galaxies, astronomers read off the ratio between its known physical size and its observed angular size or redshift separation, which yields distance and expansion information without relying on the distance ladder. Yet another gauge comes from strong gravitational lenses in which a foreground galaxy or cluster bends the light of a more distant source into multiple images. If the background source varies in brightness, the different paths the light takes introduce time delays between the images. Those delays, together with detailed models of the lensing mass, provide a measurement of absolute distances and therefore of the expansion rate. Even the ages of passively evolving galaxies can act as chronometers, because small changes in their spectra across redshift can indicate how much time passes for a given change in cosmic scale. Each method carries its own systematics and uncertainties, so confidence comes from concordance. Space telescopes such as the Hubble Space Telescope and the James Webb Space Telescope resolve Cepheid stars in distant hosts and anchor supernova distances with sharp images. The European mission that maps star positions refines the parallax rungs so that the brightness scale is not drifting. Ground surveys like the Sloan Digital Sky Survey, the Dark Energy Survey and Wide Area Spectroscopic programs chart the three-dimensional pattern of galaxies to find the acoustic feature with growing precision. New facilities such as the Euclid Mission and the Vera C. Rubin Observatory promise still deeper maps that connect the early pattern of ripples to the late-time web. When these strands are woven together, a pattern emerges in which the expansion rate today and the way it changes with time can be described by a small set of parameters, including the matter density and an energy component that behaves like a smooth field with negative pressure. This smooth component drives accelerated expansion and gives rise to an event horizon that limits future contact. The exact value of the present-day expansion rate has become a focus of close attention because different methods have produced values that are close but not identical. Distance ladder approaches that begin with geometric parallax and end with supernova yield a slightly higher rate, while inferences drawn from the ancient light patterns, combined with the standard ruler of the acoustic feature, predict a slightly lower rate when extrapolated to today. If every systematic is understood, then the difference could hint at missing physics between the early and late universe. If not, it could mark the need for better control of dust calibration, selection effects, or lens models. Teams refine their measurements with independent cross-checks. They use infrared observations to reduce the effects of dust on Cepheid brightness. They search for supernovae in hosts where multiple distance indicators agree. They develop lens models that are anchored by stellar kinematics and that are blind tested. They run end-to-end simulations for galaxy surveys to make sure that the acoustic feature is retrieved without bias. They combine weak gravitational lensing of background galaxies with galaxy clustering to test the growth of structure, because the same ingredients that set the expansion rate set the rate at which the web becomes more pronounced. In this way, expansion and structure growth become a coupled test. The present expansion rate sets the slope of the distance redshift relation near zero redshift, while the time history of acceleration bends that relation at higher redshift. The acoustic feature fixes absolute scales that tie early physics to late observation. The lensing time delays fix absolute distances on their own. When all agree within uncertainties, confidence rises that the corridor of contact through space-time is correctly mapped. When they disagree, attention turns to possibilities such as a small change in how the smooth energy evolves, a slight curvature of space on the larger scales, or new light particles in the early universe that alter the ancient light pattern. He sees how these careful numbers relate to the idea of an outside. If the present expansion rate is known, and if the acceleration is measured, then the distance to the particle horizon and the distance to the event horizon can be computed in physical units. That calculation tells how much of the universe is now in causal touch and how much can ever be. It sets the diameter of the observable region in light years and in co-moving coordinates that expand with space. It lets one estimate how many galaxies lie within view and how many remain forever beyond. It shows how the horizon will change for observers in the far future as acceleration draws distant structures away, leaving only the local group bound by gravity. Every refinement in the present rate and in the acceleration history sharpens that picture. The horizon is not a guess. It is a derived boundary drawn by data that link the brightness of dying stars, the ripples of ancient sound, the delays in lensed flickers, and the chessboard of galaxies across the sky. He understands that this work does not answer what lies outside, but it does tell how far outside begins and how the frontier shifts with time. It reveals a universe in which the concept of edge is replaced by the map of reach, a map set by the way distance and redshift marry under expansion. It also reveals that any speculation about regions beyond must respect the measured curvature, the measured rate, and the measured smoothness of the ancient light, because these numbers say whether space is open and flat enough to extend indefinitely, or curved enough to close without walls. In the quiet between observations, he lets the conclusion of this section rest on a simple thought. By measuring how quickly space stretches today, and how that rate has changed across cosmic history, observers convert the night sky into a ruler and a clock. The ruler spans from here to the particle horizon. The clock ticks both backward to the first light and forward to the event horizon that no message can cross. With each new calibration, the ruler grows less fuzzy, the clock grows more precise, and the edge of the observable universe becomes not a mystery of belief, but a boundary drawn in numbers and light. Inviting the next question about what, if anything, imprints itself from beyond that quiet line, he asks what space itself looks like on the broadest stage because the answer shapes every meaning of outside. Geometry on the larger scales is not a simple matter of drawing triangles on paper. It is a question of how straight lines behave across distances so vast that only the oldest light and the farthest galaxies can whisper the truth. In a nearly flat cosmos, the angles of a huge triangle add up to a neat straight angle. Parallel lines stay parallel, and volumes grow as the cube of their linear size. In a positively curved cosmos, which is often pictured as a higher dimensional cousin of a sphere, large triangles have angle sums greater than a straight angle lines that begin parallel may meet, and the total volume can be finite. In a negatively curved cosmos loosely imagined as saddle, shaped the angles of large triangles add to less than a straight angle, parallels diverge, and volumes increase faster than in the flat case. These are not idle distinctions. They decide whether the universe can be finite without borders, whether long journeys return to their origin, and whether an outside is a misreading of a loop. He weighs how one measures such enormous properties. The ancient afterglow carries a preferred pattern of ripples born in the hot plasma of the early time, and the apparent sizes of those ripples on the sky depend on geometry. If space is positively curved, the ripples look larger than expected because light rays converge. If space is negatively curved, they look smaller because rays diverge. Observatories that map the temperature patterns and polarization of the ancient glow see a sequence of peaks whose angular placements and relative heights are exquisitely sensitive to geometry, as well as to the cosmic ingredients. The preferred scale sits where a flat geometry predicts with room, left for a very gentle curvature that could still hide in the uncertainties. Large surveys of galaxies add a second test by locating the fossil ripple in the three-dimensional clustering of matter. When this standard ruler is compared with its appearance in the ancient light, the combination ties early physics to late structure and tightens the leash on curvature. In quiet language, the cosmos looks very nearly flat with a curvature radius that would be far larger than the observable region, even if it is not infinite. This finding allows two paths for the idea of outside. One path says that if space is truly flat on all scales, then it may extend without bound, and what lies beyond the horizon is simply more of the same kind of space that has not yet exchanged signals with here. The other path says that a space can be finite yet unbounded if it is positively curved, or if it has a multiply-connected topology, so that travel in one direction long enough brings a return from the other side with no wall crossed. In such a world, the word outside points nowhere, even if total volume is limited. He pauses on topology, the quiet cousin of curvature, because it refines the question of edges in a subtler way. Topology concerns how space is connected, not how it bends. A familiar flat surface like a square can be glued edge to make a torus, a donut shape, where a traveller who leaves through one side reappears at the opposite side. The local geometry of a small patch remains flat, but the global connection changes the experience of space. Generalizing to 3 dimensions, one can build many topologies that are locally flat or locally curved, yet globally wrap around. If our cosmos has such a multiply-connected form, light could loop around and produce repeated images of the same distant structures in different directions or repeated patterns in the ancient glow. Researchers search for pairs of circles in the ancient light that share identical patterns, as would happen if the last scattering surface intersects itself in a wraparound space. They also hunt for unusually repeating motifs in the large-scale distribution of galaxies. No decisive repetition has been found so far which pushes any wraparound scale to be larger than the observable diameter, but the absence of a detected loop does not close the case. A universe that is flat enough and large enough can hide its topology beyond today's reach, leaving the possibility that outside is only a farther copy of inside folded back on itself. He considers the meaning of finiteness without borders, because it speaks directly to the intuition that outside must exist. On a 2-dimensional sphere there is no edgeline one can stand upon, yet the total area is finite. A 3-dimensional analogue could hold a finite volume without any boundary surface. If the large-scale geometry were exactly such a closed form, the total number of galaxies could be finite, and yet every vantage point would seem central and edgeless. The horizon would still be real, because light needs time to travel, and space can accelerate, but it would not mark a step toward a final wall. It would be a step toward a curve that bends back. In contrast, if space is open and infinite, then outside the horizon lies an unending expanse of additional regions, most of which will never be in contact with this one because of the event horizon born of acceleration. In both cases, edge gives way to connection and reach. Only the texture of the beyond changes closed and repeating or open and ceaseless. He reflects on another gentle thread. Geometry and topology also guide how the largest patterns in the ancient light should behave. If the total volume of the cosmos within our view is small compared with the curvature radius, then the largest angular modes are suppressed, leading to a slight lack of power on broad scales. Some maps of the ancient glow hint at such a lack, together with alignments that place the broadest patterns along similar axes. These could be statistical accidents, or they could be whispers of a curved or connected global shape, or they could be imprints of foreground effects that are not yet fully modelled. With patience, new maps, wider frequency coverage, and better removal of local emissions will help. Until then, the suggestions keep the door open to geometries that flicker at the limits of present reach. He ties this back to the lived act of observation. The determination that space is very nearly flat arises not from a single measure, but from a web of them, the preferred acoustic scale in the ancient glow, the fossil ripple in galaxy, Clustering the lensing of background light by foreground structure, the relation between distances measured by standard candles and standard rulers, and the growth of the cosmic web. Each method leans on different physics and different sources of error. As they converge, confidence grows that we are reading a true property of space, and not a coordinated misdirection by systematic effects. If a small positive curvature survives future scrutiny, it will set a very large but finite horizon for total volume, and will strengthen the picture of a world that could be finite without borders. If the last doubt falls and perfect flatness endures, it will reinforce the idea of an endless expanse, in which the only limits are those set by time and acceleration. In either case, the question of what exists outside the edge becomes a question about how far geometry and topology allow space to continue, and whether our region is a single patch of a larger fabric whose weave never ends, or a looped tapestry in which unseen repeats lie just beyond today's light. He lets the section rest on a calm assertion that carries the mood of the inquiry. Geometry on the larger scales does not answer the mystery, but it narrows the shapes that mystery can take. It tells whether the road can circle back or head on forever, whether far-away light might return with a familiar face, and whether the word outside is a mistaken language rather than a truth about space. The measurements so far lean toward a broad flatness that leaves the compass open and the horizon provisional. The next maps will tighten or loosen that lean. Until then, the edge remains a matter of reach, and the shape of what lies beyond keeps its quiet hold on the imagination by refusing either a final boundary or an easy infinity, balancing instead on the fine line between an unbounded loop and an endless plane. He studies the sky for quiet irregularities that could hint at structure or physics pressed close to the horizon of what can be known. The ancient afterglow is almost even yet on that calm field. Tiny ripples carry subtler oddities. One famous case is the cold spot, a broad region, a little cooler than average when the map is smoothed over a wide angle. Full-sky spacecraft see it later. Maps confirm it, and so he asks what could make it. A very large, underdense region along the line of sight could drain a little energy from passing photons as the cosmic expansion changes the depth of its gravitational well, a late-time imprint of structure on ancient light. Deep galaxy surveys have searched for a vast emptiness that could account for the full depth and width of the patch. Some find hints of wide, underdense zones that may contribute, yet the size required is extreme, and the match is not exact. Another path is that the patch is simply a tale of chance in a field of nearly Gaussian ripples. In a random field, outliers must exist, and statistical studies differ on how unlikely this one is, because the answer depends on definitions of size, depth, and filtering. Thus, the cold spot sits where chance foreground structure and new physics all remain viable, with chance holding the simpler ground. He widens the view to other large-angle curiosities. When the ancient light is decomposed into patterns that span the whole sky, the broadest modes appear to show odd alignments, as if their axes cluster more than random draws would allow. The severity of this effect shifts with data treatment, with masks that remove the bright plane of the Milky Way, and with how one models faint emissions from dust and synchrotron radiation. Some ideas beyond the standard early picture predict preferred directions caused by slight anisotropy during the first accelerated growth, or by relic fields that survive to later times, leaving a global tilt. Yet small residuals from local foregrounds or subtle systematics from scanning or beam shapes could produce a similar tilt. At present, the weight of evidence leans toward caution. The alignments are intriguing but not decisive, and their interpretation is tied to the cleaning of the sky. A related claim is that one hemisphere of the sky carries slightly more power than the opposite hemisphere, at large scales a dipolar asymmetry that seems to pick a direction. Here again the details matter. How one defines hemispheres, how one selects angular bands, and how one estimates uncertainties can move the significance. Cross-checks between independent maps reduce the odds that the pattern arises from a single instrument, yet cannot fully rule out residuals from the galaxy or from zodiacal light. Still, a modest hemispherical imbalance recurs often enough to motivate new missions with different scanning rhythms and wider frequency coverage. He notes another whisper that the broadest patterns may favor one mirror symmetry over the other. In a statistically isotropic field, the balance of even and odd mirror modes should be neutral. Analyses sometimes find a gentle linear parity anomaly that again hovers between strong claim and curious hint. Because these anomalies live at the largest angular scales where few independent modes exist, chance plays a large role. But these are also the scales where global geometry and topology would leave their clearest signs. If space has a multiply connected shape, repeated sky patterns or matched circles could arise. If space is slightly curved on very large scales, power on the broadest modes could be suppressed. Neither signature has been decisively seen, but the anomalies keep that door open. He returns to the cold spot and considers a speculative route. If our bubble once brushed another region during or after the first accelerated growth, a gentle bruise might appear in the ancient light wider than most features and with a soft radial profile. Searches for circular scars or broad gradients tied to such an encounter have set limits, but have not delivered a clean detection. The cold spot is tested against these templates with ambiguous fits. His posture remains steady. Extraordinary claims need robust templates, wide frequency coverage to remove dust and gas, and blind analyses that do not tune parameters after seeing the maps. Until such work settles the question, the cold spot remains a low murmur rather than a shout from beyond. He turns to the late-time path from the last scattering surface to the telescope because it is not empty. Foreground clusters and voids gently lens the ancient photons, slightly blurring the acoustic pattern and adding distortions that can be reconstructed. This reconstruction is now measured with high confidence and matches the pattern expected from the growth of structure seen in galaxy surveys. Such concordance strengthens the case that the largest anomalies are not artifacts of unmodelled lensing. It also allows a cleaner separation of late-time imprints from early physics, so any remaining large-scale oddity must face a sharper question: does it belong to the beginning, to the line of sight, or to chance? Cross-correlations add one more piece. If very large voids or superclusters imprint the ancient light by changing photon energies as they traverse evolving gravitational wells, then maps of the nearby universe should correlate weakly with maps of the ancient light on the largest accessible scales. Modest correlations have been reported suggesting that a portion of the large angle pattern comes from known structures along the way, supporting the idea that the cold spot and its cousins may be partly local in origin, though likely not entirely so. All of these tests feed a simple stance: data first, then anomaly, then mystery, then speculation. The data show a sky whose early ripples follow a smooth start and gravitational growth, yet with a handful of broad curiosities that refuse to vanish under repeated checks. The anomalies matter because they live at the scales where any imprint from beyond our patch would be easiest to see, but they are also hard because those scales offer the fewest independent rolls of the cosmic dice. The mystery is whether the patterns are natural accidents, the residue of foregrounds, and scanning the hint of unusual geometry or topology, or the trace of contact with other regions in a larger inflating backdrop. Speculation remains measured. He keeps options open without choosing one, and he looks to new maps that watch across more frequencies, scan with different rhythms, and measure polarization with greater care. Polarization, especially the gentle twist that gravity waves from the earliest moment would induce, offers an independent handle. If a broad alignment or a cold region appears in both temperature and in the correct polarization pattern, chances rise that the origin is rooted in the beginning rather than painted on later by foregrounds. If instead temperature oddities fade while polarization remains clean, the case for chance or for local contamination grows. In either outcome, the approach to the edge gains strength because the process sorts signal from story. He ends with a calm understanding. The broad sky carries both harmony and small dissonances. Each irregularity is an invitation to look harder at the limits of the observable, and to test whether the word outside has left a fingerprint on the oldest canvas we can see. For now, the fingerprints are faint and smudged. They do not overturn the smooth blueprint, yet they keep the frontier alive, encouraging the thought that what lies beyond the horizon may be simple continuation, a gentle change in rules, or a neighbour that once came close enough to brush the paint before the universe grew apart. He surveys reports of immense architecture at the far reaches of current maps, because the size and coherence of these claimed features press on the quiet assumption that beyond some very large scale, the universe becomes smooth. In the standard picture, gravity molds matter into a web of filaments, sheets, and clusters separated by wide voids, but as one steps to larger and larger yardsticks, the contrast should fade and the average should settle. Observers call this the scale of statistical homogeneity, and models set it at hundreds of millions of light-years with some blur because of cosmic variance and the limited volume that any survey can cover. Yet deep catalogues of galaxies and energetic quasars have at times revealed ridges, walls, and long chains that seem to stretch across distances that approach or even exceed those homogeneity expectations. The first feeling when one sees such a map is awe. The second is caution. Awe because sky plots filled with coloured points trace rivers of structure that seem to cross the cosmos without care for human categories. Caution because surveys are not neutral eyes. They depend on how the telescope scans how bright the sources must be to enter the list, how redshifts are measured, how incomplete slices are handled, and how distance distortions from peculiar velocities are corrected when turning redshifts into positions. A famous example is a long wall of galaxies seen in early spectroscopic maps that chart one slice of sky. Its span measured along the slice appears to challenge the expected size of coherent features. Later analyses show that filamentary networks can align by chance along the slice direction, and that slicing through a three-dimensional web can enhance the apparent unity of what are in full view several structures lined up like beads. Other reports speak of large quasar groups at redshifts when the universe is younger. Quasars are rare points of bright activity in galaxy centers powered by accreting black holes, and their numbers and clustering change with cosmic time. If a group of them lies close in redshift and on the sky, one can infer a common large environment or even propose a superstructure. But the rarity and brightness of quasars introduce selection that can clump detections unevenly, and the methods that link neighbours into groups can percolate through the field and connect what is not truly bound. Analysts have tested whether random distributions, when put through the same grouping algorithms and masks, can produce apparent mega-groups of similar size, and the answer is often that they can, though not frequently. The tale becomes a matter of how many such giants one expects by chance in the volume surveyed, and whether the observed count is truly surprising. Still other claims resemble a grand wall or a vast arc of gamma-ray bursts events that flash for a short time and can be seen to great distances. Here the uncertainties grow larger because the selection of events depends on instruments with varying sensitivity on limited sky exposure and on complex thresholds. Patterns can emerge in sparse data that later additions erase. He does not dismiss these announcements. He places them in a patient frame. The web of structure is real, and gravity loves to draw long filaments. Simulations that begin from inflationary seeds and evolve with cold collisionless matter and a smooth accelerating component produce vast networks with nodes where clusters form and strands that cross voids. These networks include long features that can run for hundreds of millions of light years, and in a universe with billions of such stretches, a few will be exceptional. The question is whether the reported extremes demand new physics or fall within the tail of a known statistical spread once survey effects are included. Independent checks help. When a claimed feature appears, he asks whether it is seen in different catalogues with different selection rules, whether its signal stands when the sky is cut differently, and whether its extent persists when distance estimates are sharpened. He asks whether the same region shows enhanced weak gravitational lensing that would trace mass independent of light, or whether the pattern is an illusion of galaxy bias where active sources overrepresent the underlying mass. He considers redshift space distortions the way peculiar motions flatten or stretch patterns along the line of sight. Finger of God effects can elongate clusters in redshift space, while coherent infall can compress large scales, both of which can be misread as unusual length or coherence if not modelled. He also looks at the empty partners of these giants, the large voids, because an uneven universe should show both over and under. Voids leave signatures in how they lens background light and in how they imprint the ancient afterglow through the late-time shift of photon energies as the void evolves. Concordance between void catalogues, lensing maps, and subtle cross-correlations with the ancient light strengthen the case for real large features even if they remain within expectations. Beyond the catalogues, theory provides a sober yardstick. The distribution of structure sizes follows from the statistics of the early fluctuations and their growth under gravity. Large extreme structures are not forbidden. They are only unlikely. The rarity grows sharply with size, so a few massive alignments in a huge survey can appear without shaking the model, but a systematic excess of giants across independent volumes would. That is why future surveys that map a much larger fraction of the sky and probe deeper in time are so essential. They reduce the whims of small sample size average over local peculiarities and turn dramatic outliers into either expected tales or true challenges. He reflects on what these questions mean at the edge. If claimed walls or arcs near the bounds of the observable region were both real and too large to live in the present framework, they might hint that the early conditions are not as random and simple as assumed, or that global geometry or topology suppresses or enhances certain modes, or that an encounter with another region impressed a pattern that grew into a superstructure. But each of those routes would carry other consequences, from changes in the statistics of the ancient light to distortions in polarization patterns, or to repeated images from wraparound space. Those signs are not decisively seen. More modestly, the larger structures may sit near the edge simply because survey volume grows with distance, and because projection effects and selection bias become more severe in the faint outer reaches of detection. In that light, the impression of a boundary crowded with giants could be a mirage cast by volume and sensitivity rather than a physical curtain. He holds to the steady path. Data first anomaly, next mystery after speculation last. The data reveal a universe that builds a web with strands and walls on enormous scales, matched well by simulations that begin with a smooth early spectrum of ripples. The anomalies are vivid announcements of features that appear to run longer and hold together more strongly than the usual web lines. The mystery is whether these features are rare but acceptable or signs of a deeper rule. Speculation watches for consistent multi-probe confirmation and for footprints in independent messengers. He ends the section with a tempered image. Picture the largest maps as coastal charts drawn from cliff tops along a foggy shore. From each headland the shoreline seems to curve in grand arcs. As more headlands are surveyed and the fog thins, some majestic arcs resolve into chains of bays and capes, while a few remain truly sweeping. The cosmos may be the same. It draws long, graceful features that at first glance look beyond the expected, then dissolve or persist as measurements improve. Whether near the horizon there stand structures that exceed ordinary growth, or whether appearance flatters them is not yet closed. What lies outside the edge in either case is not a wall of stone but the continuation of a web, whose longest strands thread beyond sight, set by rules that current data almost capture, and that future surveys will bring into steadier view. He turns his attention to the veils between the last scattering surface and the lens of the telescope because everything between them can tint the view of the edge. Gravity gas dust and magnetic fields leave small marks on light that travels for billions of years, and those marks must be read and removed with care before any claim about horizons or beyond can stand. Gravity first. Massive clusters and long filaments of matter, both luminous and dark, warp the paths of passing photons in a quiet way that stretches and twists the images of distant galaxies. This weak gravitational lensing is not a flaw but a tool because the very distortions it causes reveal the hidden mass that would otherwise be inferred only by its pull. By measuring the subtle alignments of background galaxy shapes across wide fields, surveys trace a projected map of the matter between here and the far edge of visibility. The pattern agrees with the late-time growth of the web that simulations produce from a nearly scale-free set of early ripples, and the agreement gives confidence that lensing can be modelled and subtracted when the goal is to see the oldest light as it once was. Yet lensing also smooths and slightly blurs the ancient acoustic pattern, dragging power from one angular scale to its neighbours. Mapmakers now reconstruct this lensing field directly from the ancient glow itself, by noting how the normally random small ripples appear gently remapped. Removing that lensing blur sharpens the original peaks, and allows a cleaner look for delicate signatures such as a faint twist in polarization. The same reconstruction can be cross-checked against galaxy surveys and against the weak lensing of galaxies tying three distant pictures into one. Next comes gas, clusters that sit between the last scattering surface and the observer host hot electron clouds that nudge the energy of passing photons. When ancient photons scatter off these hot electrons, they gain a bit of energy, a small upshift that leaves a spectral imprint known as the thermal Sunyaev-Zeldovich effect. A separate effect arises when bulk motions of cluster gas give the photons a slight push or pull that depends on the motion, the kinetic Sunyaev-Zeldovich effect. Both signals are now detected across hundreds of massive systems, and both can masquerade as primary structure in coarse maps, if not carefully modelled. By measuring the frequency dependence of the sky, and by cross-correlating with cluster catalogues built from X-ray observations and optical richness, observers isolate and remove these secondary drapes from the primary canvas. The work does not end with clusters. Diffuse gas in filaments that tie clusters together also scatters light and leaves a faint web of secondary signals. Stacks of galaxy pairs have revealed hints of this warm-hot intergalactic medium by summing the small imprints along many filaments until the whisper rises above noise. As these techniques mature, they will turn a nuisance into a tracer, teaching how much ordinary matter lies outside galaxies and how it flows along the strands of the web. Dust stands as the most familiar veil and the most stubborn. Within the Milky Way, dust grains aligned by magnetic fields emit polarized light at millimeter and submillimeter wavelengths, and they also scatter and redden, the starlight that surveys use to chart galaxies. The polarized glow of dust can imitate the delicate twist pattern that gravitational waves from the first instant might leave in the ancient light. Wide frequency coverage is the answer because dust emission changes with frequency in a way that the primary ancient signal does not. Sky maps made at many bands allow a fit that teases apart the mixture of dust and primordial light. Careful masks remove the bright plane of the Milky Way, but faint cirrus clouds spread farther than one might hope, so the residual needs to be characterized, not wished away. Neutral hydrogen gas adds another layer by emitting at a specific radio wavelength, and the extended glow from our galaxy and from distant galaxies can enter experiments that seek to measure the large-scale structure through this line. Again, the remedy is not a simple subtraction, but a patient construction of a model that learns the spectral and spatial behavior of the foreground and leaves behind only what the cosmos imprinted long ago. There is also dust nearer to home. Sunlight scatters off grains spread through the plane of the solar system, making a soft zodiacal glow that varies across the year as Earth moves. That glow can mimic large-scale gradients on the sky, if not tracked and removed. Instruments on spacecraft carry orbits and shielding designed to reduce such contamination and analysis. Pipelines subtract models that follow the geometry of the solar system and the annual rhythm of the data. Even after dust and gas are accounted for the Earth itself, and the atmosphere can press a fingerprint on ground-based measurements. Water vapor temperature swings and instrument beams that change shape with time all introduce patterns that might echo the broad modes where claims of unusual alignment or low power are made. The answer here is redundancy and cross-checks. The same sky measured from the high desert, the polar plateau, and from space with different detectors and different scanning strategies should agree within uncertainties if the sky is honest and the pipelines are clean. When independent maps converge, confidence rises that what remains after foreground removal is truly cosmic. Not every shadow dims, some reveal. Foreground clusters and filaments imprint the ancient light by changing photon energies as the overall gravitational field evolves, with the accelerated expansion, an effect known as the integrated Sachs-Wolf imprint. This effect is strongest on the larger scales and during the recent era when acceleration dominates. Cross-correlations between maps of nearby large-scale structure and the ancient light show small yet consistent signals that match this expectation. The match confirms that the same smooth component that drives acceleration also leaves its gentle mark on the river of ancient photons, and it helps separate late-time imprints from early physics. Foregrounds also aid the hunt for what lies outside by acting as natural laboratories. Strong gravitational lenses in which a single massive galaxy or cluster splits and magnifies the image of a much more distant quasar or galaxy create time delays that can be measured. Those delays, when combined with models tied to the motions of stars in the lens, yield absolute distances without relying on any step of the standard candle ladder. In that way, a foreground can calibrate the cosmic ruler used to compute the position of the horizon, turning a local distortion into a measure of the global stretch. All of these layers together teach a single habit of mind. One must never skip from map to mystery without tracing the corridor of shadows that light has walked. A cold region may be cooled further by a void in the foreground. A broad alignment may shift when the galaxy masks expand. A faint twist in polarization may fade once a dust filament is modelled with the correct spectrum and orientation. The discipline is not to erase anomalies by force, but to test them against every known veil. What survives such testing is rare and precious, because it holds a better chance of being written in the first language of the cosmos, rather than scribbled by the pen of a later hand. This is why teams spread instruments across mountaintops, balloons, and spacecraft, why they observe at many frequencies, why they swap the order of operations and use blind pipelines, and why they invite independent groups to try to break their claims. The edge does not appear as a pure line. It reveals itself as a boundary drawn after every foreground shadow has been accounted for. In that cleaned picture, the ancient light still shows near perfect uniformity, seeded with tiny ripples. The cleaned picture still carries small whispers at the largest angles that may or may not be chance. The cleaned picture still bears the lensing blur that can be removed to see more clearly, and the cleaned picture still leaves room at the horizon of interpretation for hints that our region could be one part of a larger quilt, even if no stitch from another patch has been proven. He lets the thought settle. Foregrounds and lenses do not block the way to the question of outside, they are the way. Each veil once understood becomes a window. Each shadow once modelled becomes a guidepost. By travelling this corridor with patience, observers turn a sky crowded with local effects into a near-transparent sheet, behind which the first messages shine. Those messages still speak of a horizon set by time, not by a wall, and they still leave open the quiet possibility that beyond our reach the same process continues or changes slightly or meets a neighbour. The path to that answer passes through every veil, and each veil when lifted leaves the edge sharper and the wonder intact. He turns from curvature to connection because even a space that is locally flat can be globally strange. Topology studies how regions are stitched together, not how they bend, and on the largest scales that stitching can hide in plain sight. A familiar two-dimensional example begins with a square whose opposite edges are glued so that stepping off one side returns from the other. The paper becomes a torus. Locally straight lines and small triangles still look flat, but globally paths loop without borders. In 3 dimensions, many such constructions exist, some built from flat tiles, some from positively curved tiles, some from negatively curved tiles. If the universe has a multiply connected shape of this kind, and the wraparound length is smaller than or comparable to the size of the observable region, then light from a single distant object can arrive along different routes and paint repeated images across the sky. Distant patterns could then echo, and the oldest light could display matching circles where our last scattering sphere intersects itself in the wraparound space. He imagines how such pairs of circles would appear. The ancient afterglow is a shell of earliest visible light centered on the observer. If the shell meets itself because space folds, then identical temperature and polarization patterns would trace 2 circles at the same angular radius in different directions. The angles between the circles, their radii, and the way the patterns correspond would encode the specific topology. Searches for these matched circles have scanned full sky maps delivered by space observatories with steadily improving sensitivity and resolution. They compare every possible circle pair across many radii, allowing for relative twists that different identifications might impose. Thus far, no compelling matched sets have survived all tests and all foreground cleaning, which pushes any wraparound scale to be larger than the diameter of the observable region. But such limits still leave wide room for spaces that loop on scales just beyond sight, and they leave open the possibility that a modest positive curvature could be combined with a specific compact shape to generate delicate large-angle features observed in the ancient glow. He considers a proposal that once drew attention, a dodecahedral space inspired by the idea that the largest modes of the ancient light seem weaker than expected and somewhat aligned. In this picture, the universe resembles a positively curved space in which opposite faces of a 12-faced figure are identified with a twist. Such a compact shape would truncate the broadest waves that fit across the cosmos and could, in principle, reduce large-scale power and produce pairs of circles. Later maps with better frequency coverage and more careful removal of galactic emission lowered the weight of this case, yet the exercise teaches how topology can leave specific fingerprints that can be hunted in a principled way. He turns next to the way topology would ripple into the late-time sky. If light wraps, then distant galaxies and quasars could appear more than once with the same intrinsic properties, but at different redshifts because each light path has a different length. One might then search for ghost images, repeated groups and clusters seen at correlated positions, with similar internal structures and spectra, adjusted for the time delay between paths. This is challenging because evolution changes galaxies. Selection effects vary across surveys and weak lensing. By foreground structure distorts shapes. Still, one can ask whether statistical correlations between widely separated sky patches exceed what a simply connected model allows. Another route, sometimes called cosmic crystallography, tallies separations between pairs of objects to look for spikes at preferred scales that a repeating fundamental domain would introduce. These methods have delivered constraints rather than discoveries, often limited by survey depth, angular coverage, and the need for uniform selection. He thinks about polarization as a more robust test. Temperature maps of the ancient light suffer from foreground confusion that can mimic large-scale alignments or suppressions. Polarization carries additional structure. A multiply-connected topology would reproduce not just temperature patterns, but also the specific alignment and twist of polarization along the matched circles. As experiments measure polarization with higher sensitivity and broader frequency coverage, the circle search in polarization becomes a sharp wedge. A true matched pair would share both intensity ripples and polarization directions with the correct phase relationship. A chance alignment would not. He also notes that topology interacts with curvature in subtle ways. In flat three-dimensional geometry, there exist many compact shapes topologically distinct from the simple three-torus, and in positively curved geometry, there is a rich family of spherical spaceforms where finite groups identify points. Each option sets a distinct length for the fundamental domain and a distinct catalogue of allowed vibrational modes. In the ancient glow, this appears as a set of discrete large-angle harmonics, with some modes absent and others enhanced. Large-scale anomalies that hint at missing broad modes could be read as support for a compact space, but they could also be statistical flukes or remnants of imperfect foreground subtraction. That ambiguity keeps the case open but unproven. He asks what it would mean for the question of outside if space were compact without borders. In such a world there is no place beyond the edge because there is no edge to cross. The total volume could be finite, yet every geodesic eventually returns. The particle horizon remains a limit of contact set by finite time, and the event horizon remains a limit set by accelerated expansion, but the global map contains no outside. What lies beyond the horizon would then be more of the same region, revisited in different directions and at different times, with repeated patterns hidden by noise and evolution, unless the wraparound scale is small. By contrast, if space is simply connected and flat or negatively curved, then it may continue without bound, and the word outside points toward domains that are causally disconnected rather than physically separated by a wall. In that case, topology does not erase the outside. It refines what outside means by telling whether journeys loop or run forever. He weighs detection limits because absence of evidence may be only evidence of distance. Current circle searches rely on sky coverage frequency bands and angular resolution set by past and present instruments. Dust emission in the Milky Way complicates the largest circles, which are also the most informative about compact spaces. The smallest circles demand exquisite resolution and low noise. The window where matched circles would be easiest to see could fall just outside present capability. Future missions designed to map polarization across many bands with low systematics may lower this window and either reveal matched patterns or push the fundamental domain far beyond the present horizon. He also imagines a different signature, a specific drift of distant patterns produced by our motion through a compact space. If the universe loops with a scale not too much larger than the visible diameter, peculiar parallax on cosmological scales could slowly change the relative positions of repeated features across many decades. Such a measurement is far beyond present reach, but sits conceptually in the toolbox of future very long baseline astrometry. He brings the strands together into a single habit of thought. Geometry from the pattern of acoustic peaks says that space is very nearly flat across the patch we can see. Topology asks whether that nearly flat patch is part of an unbounded expanse, or whether it closes on itself in a way that hides borders. Matched circles, ghost images, spikes in separation statistics, discrete large-angle harmonics and precise polarization correlations form a suite of tests that turn the philosophical question of edges into a practical program. The present score favors a space whose wraparound scale, if any, lies beyond the observable diameter, but the sensitivity of the test grows, and the maps of polarization now in hand and soon to come will press farther. He closes the section with measured wonder. Topology does not insist on an outside, and it does not forbid one. It reshapes the question. If the universe is compact, then the edge is a misreading and the beyond is a return. If it is unbounded, then the beyond is real but out of touch. In either case, the oldest light remains the guide. It encodes the allowed patterns that space permits, and by reading those patterns with patience, he inches toward an answer that will either circle back on itself or open endlessly, both outcomes equally serene in their refusal to offer a final wall. He steps behind the smooth early picture into the stage that may lie underneath it, a broad backdrop in which the first accelerated growth is not a single event, but an ongoing process that continues elsewhere beyond view. The idea often called eternal inflation begins with a field that stores energy in empty space. When that field sits on a high plateau, space undergoes rapid accelerated expansion. Quantum fluctuations jostle the field slightly from place to place. In some regions, the field slides off the plateau and releases its stored energy as a hot bath of particles and radiation, a moment called reheating, that sets the starting conditions for a standard hot universe, like the one seen in the ancient afterglow. In other regions, the field remains on the plateau a little longer. Because these plateau regions expand faster than the rest, the total volume still inflating grows even as many patches finish and heat. The result is a mosaic in which pockets that stop inflating become individual hot regions, while the space between them keeps inflating and spawning more pockets. Each pocket is then a bubble universe, with its own history of cooling and structure formation, and beyond its particle horizon other pockets keep forming and drifting out of contact. He hears the quiet logic of this picture. It does not require that the whole of space began and ended its early acceleration all at once. It allows the same mechanism that explains the even ancient light and the seeds of structure to continue elsewhere, driven by quantum jitters that never entirely settle. The geometry of the inflating background is a restless sea in which calm islands appear. Within one island, observers later infer a smooth beginning, a near flat space, and a pattern of tiny ripples that match the forecast of accelerated growth followed by gravity's slow work. The island does not see the sea around it because the distance to the island's shores grows so quickly that light from other islands cannot arrive. Thus, the observable universe is like a single calm patch in a larger froth that lies beyond the event horizon. He asks how such a vast stage could ever be more than a story. Eternal inflation is a framework rather than a single precise model. Many potentials for the energy field can produce it, and some families of high-energy theories propose a wide landscape of plateau shapes, each with different valleys into which the field can slide. If different valleys end with different low-energy physics, then pockets can have slightly different constants, or particle families, while still sharing gravity and the broad rules that create galaxies and stars. The weight of this possibility rests on careful anchors inside our island. The ancient afterglow shows that our pocket experienced enough accelerated growth to be smoothed and flattened. The pattern of nearly scale-free ripples matches quantum fluctuations stretched by rapid expansion. Limits on defects such as cosmic strings and on relic particles constrain how reheating proceeds. None of these anchors demand a global mosaic, but none forbid it. They let the question stay open. He looks for footprints that such a backdrop might leave on the oldest light or on the matter distribution. One route is through rare encounters. If another pocket bubble forms within causal range and collides with our own, while inflation still unfolds around both, the boundary between them could sweep across our early sky and leave a gentle bruise, a circular region with a gradient or a small tilt in temperature and polarization. Teams have searched the full sky maps for such circular features, with blind algorithms setting limits on how often and how strongly a collision could have occurred. No decisive mark has been found. Another route is through a slight preference for one direction induced by a long wavelength fluctuation in the field that sets conditions just before our pocket reheats. That could tilt the broadest patterns of the ancient light, or give one hemisphere slightly more power than the other. Hints of such imbalances exist but are tangled with foreground cleaning and the low number of independent modes at the larger scales. A third route is through the statistics of the tiny ripples themselves. The simple models of a single field sliding smoothly predict almost perfectly Gaussian fluctuations with only small departures. Any strong non-Gaussian signal would force a change in the early physics, perhaps involving extra fields or complex motions. Present maps show near Gaussian patterns with only subtle leans that are still under debate. He considers gravitational waves as a messenger. The burst of accelerated expansion should generate a background of very long wavelength ripples in space-time. These waves imprint a telltale twist in the polarization of the ancient afterglow on large angular scales. Detecting such a twist would reveal the energy scale of early acceleration and would anchor or rule out families of potentials that give eternal behavior. Experiments in cold dry sites and in space seek this twist across many frequencies to beat down dust emission and to ensure that any detected pattern is not a foreground imposter. So far, the sky remains shy with upper limits that already exclude some simple high plateau shapes, while leaving many lower energy options alive. He also weighs the measure problem, a calm name for a deep difficulty. In a world where inflation never fully ends, there is always more volume inflating and always more pockets forming. Counting probabilities becomes tricky because any event that can happen happens somewhere, and there is no obvious neutral way to weigh an infinity of instances. Different ways of slicing the inflating spacetime can produce different answers. This is not a flaw in the local physics of our pocket, which is tested and precise, but it is a challenge for making predictions about the distribution of pocket properties across a global ensemble. Some prefer to step back and use only the predictions that refer to observations we can make within our region, such as the pattern of ancient ripples and the growth of the web, and to treat the global mosaic as a background that motivates rather than dictates. He keeps to the observational path. If eternal inflation is the stage, then our tests are local spotlights searching for seams. Bubble collisions should leave circular or arc-like imprints in temperature and polarization. Long wavelength drifts should tilt the broadest modes. A small curl in polarization would give the energy of early acceleration. Subtle, non-Gaussian patterns could signal additional fields. Absence of all these would not rule out the backdrop but would press its parameters into quieter corners. Presence of any scene by independent instruments with clean foreground removal would change the conversation from if to how. He connects this to the question of outside. In an eternally inflating setting, the region beyond our horizon is not empty and not bounded by a wall. It is a constantly growing inflating space that spins off new hot islands while preventing signals from crossing between islands once they are formed. Outside is then a map of unreachable domains, each complete in its own physics and history, all sharing an origin in the same restless field. Our horizon is a line where contact ends, not where space ends. The ocean continues, but the boat cannot sail there. He notes a quiet implication for the future. As accelerated expansion driven by a smooth energy component continues within our pocket, distant galaxies slide beyond our event horizon. The ancient afterglow fades as the wavelength stretches. The sky grows emptier of distant messages even as the local stars age and darken. If eternal inflation is true, new pockets continue to form far away, but no observer here will ever know them. The backdrop becomes a philosophical comfort or a scientific curiosity depending on taste, yet its core claim remains testable at the edges of our maps. Observers can keep seeking circles, tilts, curls, and tiny statistical fingerprints, while keeping an open mind on outcomes. He lets the sections settle with careful balance. Eternal inflation offers a serene way to extend the early mechanism that already explains much of what is seen. It turns the idea of an outside into a living expanse of other regions rather than a void. It carries disciplined predictions, some already constrained and some still in reach. It also carries ambiguities in counting and in model choice that keep certainty at bay. For now, instruments chart the near shore inside our island with increasing finesse, while the sea beyond leaves at most a faint salt on the air of the oldest light. Whether that salt ever forms a clear mark is a question for the next generation of maps. Until then, the prospect of a wider stage remains a gentle pressure on the imagination and a steady guide for where to look when asking what may exist outside the edge of the universe. He focuses the lens on encounters between expanding pockets, because if the early accelerated growth operates on a vast backdrop, then neighbouring regions may have brushed against this one before the young plasma settles into its quiet glow. In field language, bubbles of hot expanding space can form where the inflating field slips off its plateau. When two such bubbles approach their boundaries, sweep outward at nearly the speed set by the fabric of space-time, and a meeting creates a thin interface that deposits energy and bends the local pattern of expansion. If such a meeting touches the region that later becomes the observable sky, it can leave a smooth but distinct signature on the oldest light, a soft ring or broad gradient with an axis of symmetry. He imagines what that would look like on the ancient afterglow. The encounter horizon would project as a circle, whose center marks the direction to the collision with temperature changing gently across the disk, and then returning to the background outside. The profile could rise or fall depending on whether the interface advances toward or away from the observer, at last scattering, and depending on the details of reheating that follow the meeting. Polarization would carry a related pattern, with the directions of polarization vectors aligning in a way that respects the circular symmetry and shifting in amplitude across the boundary. A faint discontinuity in the derivative of temperature across the ring could appear a tell that a wave of altered expansion has passed. He considers less ideal features. Real encounters may be off-center, the interface may buckle as it crosses gradients in density, and later structure along the line of sight can lens and smear the pattern. Dust from the Milky Way can lay faint filaments over the same patch of sky, and zodiacal light can add a wide gradient that mimics part of the signal. That is why proposed searches do not rely on a single matched filter. They scan the sky with many circle sizes and many radial profiles. They test both warm and cool disks, and they run blind pipelines that do not know which directions are favored until the end. They also cross-check with polarization maps, because the circular symmetry should repeat there with a phase relationship that dust and synchrotron emission cannot imitate across widely separated frequencies. He reviews the present balance of claims and limits. Full sky maps from space missions have been combed with needlet transforms and wavelet methods that are well suited to finding round features of uncertain size. Candidate rings have appeared in early passes, some overlapping with the broad cold region already under discussion, but when deeper maps and wider frequency coverage were added, the significance fell. Bayesian approaches that compare a model with one or more collision disks against a model with none have yielded modest Bayes factors at best, often swinging back toward the no collision case once the cost of freedom in the model is counted. He does not read this as a dismissal. He reads it as an instruction to raise the bar on frequency coverage, polarization depth, and control of scanning systematics that can impose weak circular patterns. He extends the view beyond the ancient afterglow. A collision in the early time would perturb the potential wells into which matter later falls. The large-scale distribution of galaxies could then show a long wavelength gradient, or a slight preference for alignment along the axis defined by the meeting. Weak gravitational lensing of background galaxies by foreground structure could mirror that tilt. Bulk flows of galaxies might show a small drift along the same axis, and kinetic imprints on the ancient light from moving gas in clusters could align. Each of these is a very low signal measure with many confounders, yet together they form a cross-check. If a ring or gradient is claimed on the oldest canvas, then a chorus of subtle alignments in late-time traces with the same axis would strengthen the case. He weighs the dynamics of the interface itself. In some models, the boundary between bubbles behaves like a thin wall whose tension and motion shape the disturbance. In others, the difference between the interiors is small, and the interface is more like a gentle step in the value of a field across space. The wall can generate gravitational waves that travel ahead and behind, though their frequency is far below what present detectors can hear. The wall can also seed a shallow potential that squeezes or stretches the last scattering surface, changing the observed size of the acoustic pattern inside the ring. That points to another test. The preferred acoustic scale might shift slightly across the disk, not just the overall temperature. Measuring such a change demands very low noise and careful lensing removal, but it would be a powerful discriminant because foregrounds do not alter that scale coherently. He remembers a further subtlety. Our own motion with respect to the ancient afterglow produces a Doppler dipole that imprints a clean pattern across the sky. A collision aligned by chance with this motion could masquerade as a collision signature if the dipole and its higher-order leakage are not removed with exquisite care. Modern analyses subtract the measured dipole and correct for beam asymmetries that can leak dipole power into ring-like features. Ground-based instruments that observe small patches repeatedly at many angles help by breaking degeneracies between scan pattern and true sky. He thinks about the philosophy of evidence in this setting. The search space is large, the potential models span a family of profiles and sizes, and the sky offers only one realization of the ancient field. That means a fair test penalizes the freedom to fit noise and rewards signals that appear in independent data sets with the same parameters. A true encounter should have the same center and radius in temperature, and in polarization, it should appear with the same profile across frequency bands once dust is removed, and it should echo in gentle alignments in late time tracers along the same axis. Absence of any echo is not proof against, but presence of several echoes is strong support. He brings forward the far future because accelerated expansion inside our pocket slowly robs us of leverage. As the scale factor grows, the ancient afterglow stretches to longer wavelengths and fades, and the number of galaxies bright enough to trace large-scale structure within a fixed integration time declines. If encounter signatures exist, they are easiest to find now, not later. That urgency energizes new missions designed to map polarization across many bands with low systematics to perform all sky-weak lensing with high number density and to extend redshift surveys deep enough to test broad gradients and alignments. He clarifies what a positive detection would and would not say. A ring with the correct temperature and polarization pattern, verified independently and accompanied by consistent late-time hints, would be compelling evidence that this region once felt a gentle shock from a neighbor during the tale of inflation. That would not tell what lies inside the neighbor beyond the interface, nor would it reveal the full map of pockets. It would, however, convert the concept of outside from a silent hypothesis into an observed influence seen not as a direct view, but as a bruise left by contact. It would anchor the broader picture of an inflating backdrop with local data, and would push theorists to refine which potential shapes, wall properties and collision rates are compatible with the imprint. He ends with a calm statement of the present stance. The sky is rich but not yet generous with this particular signature. Searches have narrowed the allowed strength and frequency of collisions within the portion of the last scattering surface that we can see. Broad gradients and circles that once drew excitement now sit within bounds that prefer chance and foregrounds. Yet the method is clear, the tests are coherent, and the next generation of polarization maps may cross the threshold where a soft ring, if present, rises from possibility to evidence. If no ring appears, the backdrop of eternal growth remains possible but quieter, and the horizon remains a line of contact rather than a line of stone. If a ring appears, then the outside becomes a player in the story, not by showing itself but by leaving a fingerprint on the oldest image we hold. In that gentle fingerprint, the question of what lies beyond the edge would trade one shade of wonder for another, from a serene not knowing to a serene knowing that a neighbor once passed close enough to touch and then drifted forever beyond reach. He imagines a world that holds a finite amount of space yet offers no boundary to touch, because in such a world the very idea of outside is a misreading of the map. A simple guide is the surface of a sphere. A traveller can walk in any direction without meeting an edge, and after a long arc the path closes on itself, yet the total area remains finite. A three-dimensional cousin of that surface, a positively curved space with no border, can hold a finite volume and still allow straightest possible paths to loop. The rules of geometry change gently at very large scales. Triangles add more than a straight-angled geodesics that begin parallel creep together, and the complete set of allowed waves that fit across the cosmos becomes discrete like notes on a closed instrument. None of this needs a wall. There is only a shape that bends back on itself so subtly that within a small patch lines look straight, and volumes grow as expected, while on the whole the space keeps its contents within a compact total. He asks what this means for observation. If there is no border, then a beam of light launched in a straight direction should eventually return carrying the image of the place it left. That is the first romantic thought. The second sobering thought is that the universe expands and accelerates. In practice, the time required for light to complete a circuit may exceed the age of the cosmos, and the event horizon that arises from accelerated expansion can block the journey altogether. Even so, the geometry leaves traces. The broadest waves that fit into a finite space are limited in number, and that can reduce the power of the largest angular patterns in the ancient afterglow. The list of allowed harmonics is discrete, and some very long modes may be absent, which could explain a gentle deficit of broad-scale power if that deficit endures under improved maps and foreground cleaning. The absence would not be absolute silence. It would be the natural quiet of a room whose size sets which low notes can resonate. He thinks of light from distant galaxies in a compact space. If the wraparound scale is not too much larger than the observable region, then a single distant object could be seen more than once in different directions, each image a view along a different geodesic that loops the cosmos with a different length. The images would have different redshifts because longer paths carry older light. Their spectral fingerprints adjusted for aging could match. Their environments could show echoing arrangements of neighbours. In practice, this test is hard. Evolution changes galaxies over billions of years. Dust and gas tint light. Weak lensing by foreground structure distorts shapes. Surveys carry selection effects that favour certain kinds of sources in some directions. Yet the principle stands, and statistical searches for unusual repetition scales in catalogues of clusters and quasars have placed limits on how small the fundamental domain can be. He returns to the oldest light and its polarization, because a compact space with paired identifications would carve matched circles on the last scattering sphere. Each pair would share not only the same pattern of hot and cold ripples, but also the same polarization directions with a specific phase shift set by the way the edges are glued. The failure to find such circles so far pushes any compactness scale beyond the present horizon, yet dust and the bright plane of the Milky Way complicate the larger circles where the signal would be clearest. Future maps with broader frequency coverage and lower noise may sift the remaining parameter space. If no circles appear, the world may still be finite without circles if the wraparound scale is much larger than the diameter we can see, or if the identifications are subtle enough to hide among noise. He weighs the quiet difference between curvature and topology. Curvature describes how space bends locally. Topology describes how it connects globally. A space can be locally flat and globally compact if opposite faces of a three-dimensional block are identified, producing a torus-like world with no edge. A space can be locally positively curved and globally compact in many ways beyond the simple three-sphere each, with a distinct catalogue of allowed harmonics. A space can even be locally negatively curved and still be compact through complex identifications, though the mathematics grows more intricate. Each choice alters the pattern of very broad modes and the possibility of repeated images, and each is a way to have a finite cosmos that offers no border to press against. He brings the discussion down to a patient comparison with data. The pattern of acoustic peaks in the ancient afterglow sits where near-flat geometry predicts, and that leaves only a gentle positive curvature, if any, with a radius much larger than the observable region. That does not forbid compactness, but it pushes its scale far away. Large-scale alignments and low-power hints in the ancient light have inspired specific compact models such as a dodecahedral identification that would reduce the longest modes and imprint match circles with a twist, but improved maps and foreground control have weakened the case. Even so, the tests are clear. Seek circles, seek repeated structures, seek spikes in separation statistics, seek discrete harmonics, seek polarization matches. Each test either finds a mark or raises the lower bound on the size of the fundamental domain. He asks how a finite but unbounded world reshapes the meaning of outside. In such a world there is no place beyond. The particle horizon still exists because light has had only so much time to travel. The event horizon still exists because accelerated expansion limits who can ever talk to whom. But beyond those horizons one does not enter new territory, in the sense of a beyond that sits outside a border. One enters parts of the same world that could in principle be reached again and again along looping geodesics, if expansion did not interfere. The word outside then loses its usual force. There is only more of here inaccessible for now by time and by acceleration, not by an enclosing wall. He contemplates everyday consequences. In a finite cosmos, the night sky does not blaze without bound, not because walls block it, but because the number of bright sources within reach at any time is limited, and because expansion dims light and stretches it to longer wavelengths. The absence of an edge does not lead to an infinite glare. The interplay of finite volume evolving stars dust and the redshifting of light produces a quiet sky that agrees with experience. He imagines even the far future, as the smooth energy that drives acceleration continues to dominate distant structures, drift beyond the event horizon. The oldest light grows colder and redder. Any hope of seeing around a loop fades, not because the loop fails to exist, but because its circuit is sealed by expansion. A compact cosmos then becomes a philosophical comfort more than an observational fact. It explains how finiteness and edgelessness can coexist, and it leaves the present test to sharpen limits rather than promise a return beam from behind. He does not overclaim. The evidence today favours a very nearly flat space, and leaves compactness if present on scales beyond current reach. But the idea of finite without borders remains a coherent answer to the edge question, one that replaces outside with return. It says the universe could be a room without walls, whose floor curves back so slowly that its inhabitants never notice, except in the longest notes of its ancient music. It says that what lies beyond the horizon is not another realm, but the same realm folded by geometry and hidden by time. It keeps the mystery intact while offering a precise path for measurement. He ends with a calm statement of balance. Finite without borders is neither demanded nor excluded. It is a frame that honours the data, respects the near-flat shape measured so far, and translates the old urge to find a rim into a new habit of reading modes, matches and circles. If the circles appear, the room will be shown to loop. If they do not, the room may still be endless. In both outcomes, the question of outside becomes a question about connection, and connection is a matter not of walls but of signals, and of the gentle architecture of space itself. He asks what can speak from beyond the reach of light, because photons are not the only messengers, and the surface from which they last scattered is not the first screen the cosmos can paint. Before neutral atoms form photons, ricochet in the hot plasma, and cannot travel freely, but other particles with weaker interactions slip away earlier. Neutrinos decouple when the universe is about 1 second old, leaving a bath of relic neutrinos that today should be cooled to a temperature of about 2 Kelvin and drifting through every cubic centimetre of space by the hundreds. Detecting this cosmic neutrino background directly is hard because neutrinos barely touch ordinary matter, yet experiments seek their faint pull on beta decays in cold targets, and cosmological fits already feel their presence through the way they smooth small-scale structure and alter the detailed pattern of the ancient afterglow. Neutrinos therefore serve as a messenger whose horizon lies deeper in time than the photon horizon, and their properties record conditions that precede the release of the oldest light. He then turns to ripples in space-time itself. Gravitational waves are distortions that travel at the speed of light, but do not scatter from plasma in the way photons do. Any violent motion of mass can generate them, and quantum fluctuations during the first accelerated growth should seed an almost scale-free background of very long wavelength waves that stream unhindered from the earliest fractions of a second. These waves would lay a distinctive curl called a handed twist into the polarization of the ancient afterglow on large angular scales. Instruments on polar plateaus, high deserts, and spacecraft have searched for this twist while mapping dust polarization across many frequencies to ensure that the pattern is not a foreground masquerade. Upper limits now exclude some simple high-energy shapes for the early acceleration, while leaving many possibilities. A detection would reach beyond the photon horizon to a time no other probe can see directly. He widens the range of gravitational wave messengers. Compact binaries of black holes and neutron stars produce waves with periods from milliseconds to minutes that present and near-future detectors on Earth and in space can hear. Each such merger is a standard siren because the wave signal encodes how far the source is, and when an electromagnetic counterpart reveals the redshift, the pair fixes the expansion curve without relying on a ladder of calibrations. With enough standard sirens across cosmic time, one can trace the growth of distance with redshift and test the same smooth energy that creates an event horizon, all without depending on standard candles or rulers. On still longer timescales, networks of pulsars act as a galaxy-sized detector that can sense a hum from ensembles of supermassive black hole binaries. That hum already appears as a correlated drift among the pulse times of many pulsars, a result that opens the door to mapping the growth of giant black holes, and perhaps in time to separating a primordial component from an astrophysical chorus. He steps from waves to lines written in the sea of neutral hydrogen. After recombination, the gas between galaxies is mostly neutral for a long stretch of time before the first stars and galaxies reionize it. Neutral hydrogen can absorb and emit at a radio line set by a tiny energy difference in the ground state of the atom. By measuring this line across the sky and across frequency, observers can build a three-dimensional map of the gas from the cosmic dawn back toward the Dark Ages. This tomography reaches to times earlier than the first galaxies and reveals temperature, density, and radiation backgrounds before the cosmos becomes bright. The line is faint and foregrounds are fierce, but pathfinder arrays are already mapping patches, and future instruments promise a view of structure formation from an era that photons from galaxies cannot show. He adds that the continuous spectrum of the ancient afterglow can itself hold earlier whispers through slight departures from a perfect blackbody shape. Energy released by decaying particles, or by the damping of small ripples in the early plasma before recombination, can distort the spectrum into what are called mu and Y shapes. A precise spectrometer in space could measure these distortions and thereby read an energy history from times that otherwise lie behind the photon fog. He circles back to particles that carry tremendous energy. Ultra-high energy cosmic rays and very energetic neutrinos arrive from distant accelerators, but magnetic fields bend the paths of charged cosmic rays so that they lose the memory of their sources, and interactions with background photons limit how far the highest energy particles can travel before breaking apart. Very energetic neutrinos avoid these limits and can point back to their engines, yet they are rare and imply local rather than horizon-scale messages. These messengers complement the view but do not reveal a new edge. He threads a single idea through these diverse probes. Each messenger has its own decoupling time, its own last scattering surface, and its own horizon. Photons carry the image of the universe at the time of recombination. Neutral hydrogen line maps trace the gas after recombination and before the first lights. Neutrinos carry information from about 1 second after the beginning. Primordial gravitational waves would speak from a tiny fraction of a second after the beginning. None of these cross the event horizon of an accelerating universe. Beyond that limit, no signal can ever reach here, no matter how early it departs. But within that limit, deeper messengers move the boundary of knowledge closer to the beginning than photons alone can manage. He considers how these probes cross-check one another. The number and masses of neutrino species alter both the ancient afterglow and the growth of structure, so fits that combined sky maps with galaxy clustering and weak lensing can weigh neutrinos in the aggregate. The absence or presence of a polarization curl constrains the energy scale of early acceleration and shapes expectations for the size and frequency of bubble collisions. Standard sirens measure the expansion history directly and test whether gravity on the larger scales behaves as in the theory of general relativity or deviates in ways that might hint at new fields or couplings. Neutral hydrogen maps of the Dark Ages will test how the first luminous sources heat and ionize the gas, and will measure power on scales that galaxy surveys cannot, thereby bridging the blueprint painted on the last scattering surface to the first sketches drawn by emerging structure. He keeps the meaning of outside in view. These messengers do not leap beyond the particle horizon defined for photons. They define their own horizons that can lie deeper in time. They do not bypass the event horizon that accelerated expansion raises. They bow to it. What they offer is not a path through a wall, but extra windows in the same house that open onto earlier rooms. Through those windows one can glimpse the arrangement of the early furniture and infer whether the house was built according to a simple plan or whether additions and neighbouring structures left marks. He ends with a measured promise. The next steps are clear. Sharpen the search for the polarization curl. Push the sensitivity of neutrino background experiments. Lengthen pulsar timing. Baselines fly a spaceborne spectrometer to read spectral distortions and build arrays that can map neutral hydrogen through the long quiet before the first dawn. Each step will move the line between known and unknown, not by declaring an outside, but by revealing more of the inside that precedes the oldest light. The edge then becomes not a cliff, but a layered set of horizons, each tied to a messenger, each teaching that the universe guards its earliest chapters behind different veils, and each allowing a glimpse a little farther back without ever promising a view beyond the final horizon, where accelerated expansion keeps all else forever out of reach. He projects the map of contact into the deep future, and sees how the edge folds inward as accelerated expansion continues. A smooth energy component with negative pressure drives the scale factor to grow faster and faster, and in such a world there exists an event horizon that no signal can ever cross to arrive here after a certain time. That horizon is not a wall of matter. It is a limit drawn by the race between light and the swell of space. As time lengthens, distant galaxies drift beyond this limit. Their present light continues to approach, but any new light they emit after crossing can never reach. The accessible cosmos therefore shrinks in a practical sense, even as the total universe does not. He thinks first about the whisper of the ancient afterglow. Today it fills the sky as a nearly perfect black body at a few Kelvin, the fossil glow of recombination stretched by expansion. As the scale factor grows by large factors, the wavelength of that radiation lengthens and its temperature falls. Photons become ever softer and less energetic, their number per unit volume diluting as space swells. In a far epoch, the glow slips to wavelengths so long that practical detectors cannot hear it, and eventually the ancient light is redshifted beyond any apparatus that future beings bound within a single galaxy group could devise. The oldest message fades not because it ends, but because it is stretched into near silence. He then turns to the fate of the tapestry of galaxies. Gravity holds small regions together, but on scales beyond the reach of binding, accelerated expansion carries structures apart. The same component that sets the event horizon ensures that given enough time, only the nearest cluster of bound systems remains visible. For observers who dwell within the present local group, the Milky Way and the Andromeda Galaxy and their satellites will merge through slow dances of gravity into a single massive island, sometimes called a future combined galaxy. The light of present-day remote galaxies will have passed through long before, and the new light from those systems will be forever out of touch. Astronomers born in that late age looking outward will see only the stars of their own large composite galaxy, and perhaps a few dwarf companions that never escaped. The sky beyond will be dark and nearly featureless. Without a memory of today's broader map, they might infer a static universe, or at best a small island of stars adrift in darkness. He feels the quiet sadness and the strange beauty in that prospect. The path to knowledge is not a simple line. It is a corridor that narrows with time under acceleration. He lingers on clocks and rulers in that distant future. The expansion history will be encoded in fossils. The stars in the combined galaxy will carry age distributions that record the tempo of star formation. The chemical makeup of gas and stars will reveal cycles of birth and death that depend on a past supply of infalling material. The motions of halo stars and globular clusters will carry the imprint of a dark matter, potential assembled during earlier epochs when outside structures still interacted. But the direct geometric signs of expansion, such as the relation between redshift and distance measured with standard candles, will be gone because there will be no external galaxies to serve as markers. Even the standard ruler, written by ancient sound waves into the three-dimensional pattern of galaxies, will be unavailable, because the external web will have slipped beyond sight, and the internal fossil ripples will have been stirred by long dynamical evolution. The only remaining cosmological light might be the decayed embers of the ancient afterglow, and even that will be too cold and too long in wavelength to measure. He notes that time does not erase gravity within the island. Stars continue to evolve. New stars still form from leftover gas, though the rate declines as gas is used or heated, and as fresh cold inflow ceases. Giant molecular clouds collapse and birth small clusters. Supernovae occur and seed the medium with heavier elements, while black holes in the cores accrete slowly from surrounding gas and pass the time in quiet flickers unless stirred. Planetary systems age and long-term gravitational perturbations reshape orbits. Within the island, astrophysics is lively for a very long time, but the cosmic conversation ends at the shoreline set by the event horizon. He contemplates the horizon itself in dynamical terms. In an accelerated universe approximating a de Sitter-like state, the event horizon has a fixed physical scale. It acts like a sphere beyond which events cannot influence a given world line. Thermodynamic analogies associate a temperature and an entropy with such horizons as with black hole horizons, suggesting that the horizon is not empty of meaning. Yet for the present purpose, the practical outcome is clear. The number of galaxies within contact becomes finite and then constant, and the last external messages from more distant regions are finite in number and fade with endless redshifting. He imagines a far observer asking whether there was ever more to see. Without relic records, the answer would be difficult. He realizes that we now occupy a special time not by design but by circumstance. The window to measure both the ancient afterglow and the vast web of galaxies is open wide in this era. It is wide enough to calibrate rulers and candles, wide enough to weigh the smooth energy through its effect on distances and on the late time imprint in the ancient light, and wide enough to cross-check geometry and growth. Later epochs will not have this luxury. The corridor will have narrowed too much. He asks what this inward moving edge means for the question of outside. It offers a sober lesson. Outside is not a place but a class of regions that will soon slip beyond influence forever. Today the edge is set by what light from the distant past has had time to reach us, and by what events in the distant future can ever send us news. Tomorrow, in the cosmological sense, the latter limit presses inward. The class of regions that can ever touch us shrinks to the single-bound island. Speculation about other regions becomes not only untestable, but unformulable for those future observers, because even the memory of the broader cosmos would be beyond recovery. The very idea of a horizon might be foreign. He wonders whether any traces could be hidden for them by earlier civilizations. Archives built today could preserve sky maps, distances, and spectra in media designed to last across cosmic epochs. Yet such an act would be a local kindness, not a universal law. Most fields of view will not remember. He turns to the fate of the oldest signals at a more detailed level. As wavelengths stretch, the ancient afterglow's photons eventually exceed the size of the horizon, becoming indistinguishable from the thermal bath associated with the horizon itself. The neat map of temperature variations, already faint today, dissolves into an undetectable uniform background. The polarization pattern, where we now hope to read a twist from early gravitational waves, becomes unattainable. Standard sirens from distant mergers, now a promising tool to trace expansion, will not arrive from beyond the horizon. Even the background rumble from supermassive black hole pairs, now sensed as a correlated drift among pulsars, will diminish as the large-scale assembly of structure slows and the supply of new pairs declines. The universe becomes quieter in its long wavelengths. He resists literature and holds to clear statements. Accelerated expansion draws a boundary around every place that sharpens with time. What remains within that boundary is an island of bound matter that carries its own long story. Everything outside recedes into practical absence. For the question of what exists beyond the edge, the far future answers in its own way. There is more beyond, but there is no longer any way to know it. In the present, there is a delicate balance. The maps are good enough to test early acceleration, to probe curvature, to weigh the smooth energy, and to search for seams that might indicate encounters or exotic topology. In the remote future, that balance is gone. The observable becomes the local. The cosmic becomes the parochial. He closes with a calm reflection. The horizon that matters to knowledge is not a finish line fixed in space. It is a moving front that depends on the time of the observation and on the rate at which space grows. We live near the middle of an observational era that can see both the earliest visible light and the largest connected structures. After this era, future astronomers will still read the physics of stars and gravity with elegance, but their sky will be a quieter page. The same expansion that once revealed a vast cosmos will have erased most of its letters. What lies outside will continue to exist as it always has, yet the book will be closed to their eyes, and the wonder they feel will be born not of distant maps, but of the knowledge that their island is all they can see, set inside a universe that is larger than any island can hold. He turns from maps drawn on the sky to motion through the sky because movement can become a measuring stick for the beyond. Every observer carries private frame, and the local group of galaxies drifts with respect to the ancient afterglow at roughly a few hundred kilometers per second, a speed that is small compared with light yet large enough to stamp a clean signature on the oldest glow. That motion produces a warming on the side toward which we move, and a cooling on the side from which we recede, a dipole pattern that stands out above the finer ripples. The same motion also squeezes apparent angles slightly in the forward direction, and stretches them behind a gentle aberration that shifts the apparent positions of small features. It boosts the brightness of the small scale, ripples a little in front, and dims them a little behind a Doppler, boosting that creates an asymmetry in the statistical weight of high-frequency patterns across the sky. These effects, though small, are now measured, and their directions and sizes agree with the dipole. The result is a rare fixed point in a universe of parameters, a measured speed and a measured direction relative to a cosmic standard. With that anchor in hand, he asks whether other observables carry the same mark, because any mismatch would hint that something beyond simple motion is at work. Deep surveys of radio sources and dusty star-forming galaxies count objects across the sky, and our motion should imprint a dipole in those counts as well, both through aberration on their apparent positions and through Doppler shifting of their fluxes into and out of the survey bands. Several catalogues do show a dipole that roughly aligns with the ancient afterglow dipole, though the measured amplitude has sometimes run higher than the simplest prediction, a tension small enough to invite caution and large enough to invite more data. Infrared and optical catalogues are complicated by dust in the Milky Way, which can mask or mimic a dipole, but careful masks and cross-checks can reduce that confusion. If when the dust is handled and the selections are uniform, the dipoles from independent catalogues line up in direction and size with the dipole of the oldest, the case strengthens that the observed drift is purely kinematic. If not, then either biases remain, or some large-scale structure beyond our immediate environment nudges number counts in a way that happens to align a possibility that can be tested with deeper volumes and better uniformity. He then turns to a more exquisite idea, parallax on cosmic scales and its quiet cousins. Parallax is the apparent shift in position of a nearby object against distant backgrounds as the observer moves. On stellar scales, Earth's orbit provides a baseline, and missions that map star positions with extreme precision have extended parallax out to many thousands of light years. On cosmological scales, the baselines become the slow drift of the solar system around the center of the Milky Way and the steady recession of distant galaxies driven by expansion. Over decades, the apparent positions of very distant quasars should change by tiny amounts as our velocity vector slowly rotates, and as the expansion shears angles very slightly in different directions if there is any global anisotropy. The present measurements of this secular aberration drift taken from radio interferometry that tracks compact extragalactic sources already reveal a coherent flow of apparent motions toward the galactic center that matches the expected acceleration of the solar system barycenter around the Milky Way. That success is a proof of method the sky can serve as a dynamical grid in which tiny proper motions carry information about our motion and about any global distortions. He asks what more could be read if precision climbs further. If the universe expands perfectly the same in all directions, then after accounting for local rotation around the Milky Way, and for small tugs from nearby mass, the residual pattern of quasar-proper motions should average to zero, apart from random noise. If there is a slight global anisotropy, perhaps from a very long wavelength mode in the early conditions, or from a small departure from the simpler smooth energy, then a quadrupolar flow could appear, with sources drifting in a slow pattern that picks out an axis on the sky. If spaces multiply connected on scales not far beyond the observable region, very long baselines across decades could in principle reveal a slow, relative drift between repeated features, once they are identified in pairs, a dream measurement that would turn topology from an imprint on the oldest light into a real-time geometry. The same idea extends to distances rather than angles. A class of standard candles or standardizable candles, such as certain supernovae, can be used to test whether the relation between redshift and brightness is the same in all directions once local flows are removed. Any residual directional tilt would invite a search for broad anisotropy. Standard sirens provide a complementary route because their waveforms carry absolute distances without the complex astrophysical calibrations that light demands. A suite of sirens across the sky would test the smoothness of expansion with a new ruler. He weaves in another kinematic thread that connects the oldest glow to recent structure. Moving galaxies and clusters imprint a very small temperature shift on the ancient glow when photons scatter off the electrons in their gas, a shift that depends on the line of sight velocity of the gas. By stacking many such systems, one can detect a faint pattern that is coherent on very large scales, a kinetic imprint that reveals bulk flows of matter. If those flows align with the direction and magnitude expected from the distribution of mass, mapped by surveys, the case strengthens that the large-scale structure within our horizon accounts for our motion and for the drift of nearby matter. If the flows extend farther or differ in axis, the difference could hint at deeper structures near the horizon or at features beyond it that pull on our region gravitationally, though gravity cannot send instantaneous news. Any pull must come from mass within the past light cone. This is how motion and parallax convert an abstract edge into a practical test measure, how the sky changes because we move, subtract the part that must be there, and study what remains. He pauses on the danger of overclaiming. The samples used for dipoles in number counts must be uniform across the sky, yet the sky is not a uniform laboratory. Dust varies, observing time varies, calibration varies, and galaxies evolve with redshift in ways that can couple to selection. Proper motions of distant sources are tiny and can be confounded by structure in the radio jets of active nuclei by gravitational lensing that slightly deflects paths in a time-dependent way, and by the stability limits of reference frames tied to a finite set of objects. The cure is patience and redundancy, many catalogues at many wavelengths, repeated measurements across decades blind pipelines, and comparisons between independent instruments and teams. He returns to the meaning of outside. Our measured motion with respect to the ancient afterglow is a statement about our place within the nearby web. It tells how we slide toward concentrations of mass, and its direction points roughly toward known superclusters that weigh on the local flow. If after all corrections a residual drift remained that could not be explained by the mapped mass within the accessible volume, the temptation would be to invoke pulls from structures just beyond the horizon. But gravity respects causality. Any present pull must come from something whose signal has had time to reach us in the past, even if its light has not. A residual could alternatively reflect unknown systematics or an incomplete census of dark matter within the horizon. Thus motion is a guide, not a shortcut. Parallax drift and kinematic imprints let us test whether the cosmos is globally isotropic and whether large-scale features near the edge leave coherent traces in angles and in flows. If the tests continue to agree with a smooth isotropic expansion, once local structure is modelled, then the picture of an edge defined by time and not by a wall is strengthened, and outside remains a simple continuation. If the tests find a small repeatable tilt or drift that survives every foreground and instrument test, then the edge would carry a subtle design, perhaps from an early long wavelength fluctuation, perhaps from a gentle anisotropy of the smooth energy, perhaps from a topological fold. None of these would draw a border, all would deepen the map. He ends with a steady image. The night sky is not only a picture, it is a slow film. Over years and decades the frame shifts by tiny angles, and the brightness statistics lean by tiny amounts, all because we are moving through a patterned universe. To read those shifts is to hold a ruler against the edge. Motion defines the local center, parallax tests the global symmetry, and together they bind speculation to measurable drift. In that quiet binding, the question of what lies beyond the edge narrows to what aligns with our motion, and what does not, what drifts as expected and what drifts with a mind of its own. From such slender motions seen patiently, a great deal about the beyond can be inferred without ever stepping across the horizon itself. He gathers the strongest clues and shapes them into questions that point outward, because the edge is most honest when it remains a direction rather than a destination. The first clue is the near flatness of space across the observable region, a calm result that allows either an endless expanse or a very large closed form with a radius far beyond present maps. The question is whether deeper surveys and sharper measurements will lock flatness more tightly or reveal a gentle curvature that hints at a finite but unbounded whole. The second clue is the quiet precision of the ancient afterglow, whose ripples match the forecast of early accelerated growth, and gravity's slow assembly, yet whose largest modes carry faint irregularities in power and alignment. The question is whether those irregularities fade as foregrounds are mastered, or persist with polarization patterns and frequency behavior that compel a new element in the early story or a global feature of space. The third clue is the measured acceleration of expansion traced by standard candles, standard rulers weak lensing, and soon by standard sirens. The question is whether this smooth energy behaves exactly like a constant background, or whether it drifts softly with time or direction, a drift that would sketch an axis or a slow tide on the larger scales. He then sets out the cleanest tests that near-future missions can deliver, without closing the wonder. A spaceborne mapping of polarization across many frequencies with very low systematics can search for the handed twist that early gravitational waves would inscribe. A detection would fix the energy scale of the earliest growth and narrow the families of fields that can drive it. No detection at deeper sensitivity would press those families into gentler shapes and reduce the likelihood of loud bubble collisions, while still allowing a vast backdrop that remains quiet. The same maps can hunt for matched polarization circles with a phase relationship that dust cannot mimic. Either the circles appear and reveal a compact global connection, or their absence pushes the wraparound scale farther refining outside into a longer road. A new spectrometer in space that reads the full spectrum of the ancient afterglow to exquisite accuracy can test for tiny departures from a perfect blackbody fossils of energy release before photons decouple. A measured spectral distortion would add a paragraph to the early thermal history and offer a window into processes that lie deeper than sight, clarifying whether small-scale ripples damp in a way that matches the simplest picture or require extra physics. Arrays that map the neutral hydrogen line across the sky through the long, dark ages and the first dawn will draw a three-dimensional chronicle from before galaxies brighten. Those maps can measure power on scales that link the last scattering surface to the first stars, can test the distribution of radiation backgrounds, and can probe any long wavelength tilt that might have been seeded by a very broad early fluctuation or by a gentle preference in the smooth energy. Ground and space observatories that chart weak gravitational lensing with high source density will weigh the growth of structure over time and across the sky. If growth deviates from the link to expansion expected in the standard theory of gravity, the deviation could signal new fields, new forces, or a need to revise how smooth energy behaves, each outcome altering the distance to the event horizon and the practical shape of the edge. A long baseline network that times many pulsars with higher precision will sharpen the hum from supermassive black hole pairs, and could with patience separate that astrophysical chorus from an older note, a primordial bass that carries the earlier story in a different key. Detectors in space that listen to waves with periods of minutes to hours will turn black hole mergers across cosmic time into standard sirens writing a distance redshift relation that stands independent of light and that can test isotropy when spread across the sky. Very long baseline astrometry can continue to watch the whole dome for secular drift, confirming local acceleration around the Milky Way and searching for any residual quadrupole that might hint at a global anisotropy. Deeper and wider catalogues that count radio and infrared sources in a uniform way can measure the kinematic dipole produced by our motion and compare its amplitude and direction with the dipole in the ancient afterglow closing the door to biases or opening a window to unexpected large-scale structure. He sees how these tests braid together into a discipline. Each alone can be fooled by foreground selections or systematics. Each in concert with others corners the truth. Polarization cleans temperature anomalies. Spectral precision checks energy release claims. Hydrogen tomography bridges the early blueprint to the first structures. Weak lensing ties growth to geometry. Standard sirens and standard candles review the ruler. Secular aberration drift and number count dipoles tie motion to maps. The edge then becomes a corridor lit from many sides where shadows cast by one lamp are erased by another. He also embraces the possibility that the answer is not a dramatic new feature, but a deepening of the present frame. The outside may be simple continuation, a reach that never ends in space but ends in contact built by time. If so, the work ahead will make that simplicity precise. It will measure curvature ever more tightly, pin the smooth energy more closely to a constant confirm that the broadest alignments are illusions of dust and sampling, and raise the lower bound on any wraparound scale until the idea of a local loop no longer tempts. He does not find this outcome dull. A cosmos that continues without edge, governed by rules that remain simple across scales, is a vast and quiet result. It leaves the wonder intact by making the beyond endless in the most literal way. He also allows that a small clean deviation may appear, a soft ring with a correct polarization echo, a matched circle pair that survives every mask, a tiny but repeatable quadrupole in the proper motions of quasars, a slight drift in the behavior of smooth energy. Any one of these would not draw a wall, yet each would reshape the map and the question. Outside would become not only more space, but also a structure or a rule that carries across scales a signature that this region shares a larger design. He keeps the tone steady. The path forward avoids grand conclusions and favours clear falsifiable patterns. It respects that gravity and light must carry the message that time sets the appointment and that acceleration writes the last line by limiting future contact. It acknowledges that data can overpromise and that the appetite for meaning can run ahead of the trace on the sky. It also celebrates that instruments and methods now exist to test ideas that once lived only in thought. The question of what exists outside the edge of the universe does not end with a map or with a phrase. It ends for now with a program measure, curvature measure, polarization measure, growth measure, motion measure, spectra, and measure the quiet between signals because absence is also a datum. He lets the section rest on a final image that keeps faith with the mode of this story. He stands beneath a sky that is both the earliest photograph and the farthest mirror. In that mirror he sees a boundary drawn by time and dressed by expansion. He does not ask it to part, he asks it to answer with the patterns it already holds and with those it withholds. The next instruments will open more of those patterns not to declare a final border, but to set the horizon more exactly to test whether space loops or runs on, and to decide whether a neighbour once brushed past. Whatever they find, the mystery will remain honest because it will be attached to numbers and to light rather than to wish. The edge will remain a moving front, and the outside will remain a word that means either return or continuation, each one measured rather than imagined, each one allowing the wonder to stay.